Good morning. Today we are going to be looking at elementary particle physics for quite a number of chapters now. We have been looking at fundamental particles. We've been looking at electrons, protons, neutrons, neutrinos, photons. That's kind of been the list of particles that we've been working from. And we've been looking at quantum physics and trying to get a better understanding of the properties of these fundamental particles. Well, today what we want to do is kind of go through what we call the standard model. It's the complete list of fundamental particles and our best understanding of how the forces of nature interact with these particles. So let's go ahead and get started. The picture that we have here is actually a particle detector at a particle accelerator. So this is an example of probably a proton-antiproton reaction inside a detector at an accelerator. And you can see all of the tracks of charged particles that were generated in this reaction. So so what researchers need to be able to do with something like this is an example of what's called an event. And researchers go in and use the curvature of the track. There are magnetic fields that are set up inside this chamber. They can follow the curvature of the track to be able to measure what the momentum is. There are techniques where they can measure the ionization energy of these particles. They can use this information to figure out what kind of particles they are, what was generated in these reactions, and then they look for patterns. You know, if we run this reaction many times, millions or hundreds of millions of times, what are all the different patterns that we see in these reactions? So again, this is probably coming from a proton-antiproton reaction. Now here's a picture of an accelerator. This is the largest accelerator within the United States. It's called Fermilab. The largest portion of this accelerator is this very large ring, and then over on the right is a picture of some of the researchers down inside where they maintain what's called the beam line. So if you look at this facility, you'll see that there's a series of other, there's another ring that's nearby, there are lots of buildings around. These are different sorts of accelerators, and what they're doing is, at Fermilab, the highest energy accelerator is based on protons and antiprotons. So they've got to be able to generate a beam of protons. Now that can be generated by using hydrogen. You can just ionize hydrogen and you've got a bunch of protons. But along the way they have to generate antiprotons. So one of these accelerators is generating antiprotons, and then the antiprotons have to be guided off and introduced into this ring. So the idea is, with the accelerators on the side, is to get a beam of moderately high energy protons, moderately high energy antiprotons, and send them in opposite directions. Now we've studied some of these techniques. We've looked, first of all, with electric fields. We've seen how you can use electric fields to bring particles up to speed. So to get these particles moving faster, we can use electric fields. And then we've also looked at magnetic fields. Charged particles going through magnetic fields are curved. So that gives a curved path. And that's how these protons and antiprotons are guided through this circular path. So you can see that's such a nice picture down inside. Now this is several miles in circumference. So it's a really large facility, many miles. I guess I should check and find out just how many. So you can see what it looks like down inside that tunnel. And then one of these is, so these are a bunch of magnets. And then one of these is a beam line. I'm guessing this is the beam pipe where the protons and antiprotons are being guided. And you can see that that's a pretty narrow path. So they've got to be very precise in the way that the protons and antiprotons are being guided. Now there's a couple different things we can think of going on at the particle accelerator. One of the items is, as we speed up these particles as we bring them up to higher and higher energies and higher momentum. Now from special relativity, I guess we should point out, what we learned in special relativity is that the fastest a particle can go is the speed of light. But there's no limit, really, to how much energy or how much momentum a particle could have. So a proton or an electron, as it approaches the speed of light, its energy increases asymptotically towards, or increases at a very large rate. As it asymptotically approaches the speed of light, the energy heads off towards an infinite value, as does the momentum. So as the momentum gets larger and larger, the wavelengths of those particles get shorter. Now, what does the wavelength have to do with these accelerators? Wavelength is a measure of how much resolution we can produce. So, for example, here's another accelerator facility. This is the Stanford Linear Accelerator Center just down along the peninsula. This is actually Interstate 280. Maybe you've driven through there. This is adjacent to the Stanford University campus. It's in Palo Alto, or adjacent to Palo Alto. And this is an anti-electron facility. So the first part of this accelerator was this 2-mile-long linear accelerator. So rather than using magnetic fields, at least initially, rather than using magnetic fields to create these circular paths, initially the accelerator was built back in the 1960s, I think, just to create really high energy electrons. Now, what can you do with really high energy electrons? Well, you can run them into things. And so you would take electrons, bring them up to really high speed, and then run them into, a bunch of hydrogen, for example. So what would you do in an experiment like that? Well, you would be using the high resolution of these really high energy electrons to figure out what is inside protons and neutrons. Turns out protons and neutrons are not fundamental particles. This was known probably since the 1930s. It was recognized that protons and neutrons didn't behave like simple charged particles or simply neutral particles, that there were constituents inside. And that's what these experiments were. This accelerator, in some sense, one of the main reasons for building it was to try and figure out what the protons and neutrons consisted of, and that involved going to high resolution. And so that's one of the items here, is we can get very high resolution. The electrons, instead of reacting with the protons, are going to be reacting with the particles inside the protons. And then you can make measurements of the particles that the protons are made out of. Now the second item that we want to include here is at those high energies, these particles are coming in with a lot of kinetic energy. And a lot of kinetic energy means that you can create heavier particles. Particles that you maybe haven't ever observed before could be created by using a lot of kinetic energy. So high resolution to identify particles within the protons and neutrons, and then lots of kinetic energy in order to create heavier particles. Here's an example. It says let's look at a high resolution at the Stanford Linear Accelerator Center. I threw that in Slack. That's where I was working when I was in graduate school at the University of California, Berkeley. I was part of a collaboration, and we had a pretty large group at the Lawrence Berkeley National Lab, and then we collaborated with other universities, and our experiments were based at the Stanford Linear Accelerator Center, which is another national laboratory. So it's saying here, what would the resolution be if those electrons were given a kinetic energy of 1.3 GeV? And there is the Stanford Linear Accelerator Center. So let's take a look at some of the formulas that we've already worked with, and that's pretty much what's going on in this chapter, is that we're going to be using formulas that we've worked from before. So here is the wavelength The wavelength is given by Planck's constant over the momentum. Now we can rewrite that as hc over pc, and hc now can be written as 1240, but since we're at such high energies, I'm going to write that as MeV times femtometers. Okay. Now, just how much momentum do these electrons have? And what they told us was these electrons are at 1.3 GeV, and kind of I don't think they've actually mentioned kinetic energy. That's kind of a default understanding. Yeah, they're calling them 1.3 GeV electrons. So typically that's referring to their kinetic energy. So let's see. In terms of kinetic energy, they're calling this 1.30 GeV. Now G is 10 to the 9th. GeV is 1,000 MeV. So this 1.30 GeV is the same thing as 1,300 MeV. Now the mass of the electron is only 0.000511 GeV. So if we look at the total energy of these electrons, they're totally dominated by their kinetic energy. Their MC squared value, their mass, is really negligible compared with the kinetic energy that they have. Now, if we go through and solve for the momentum, we find the very same thing, that once you get to these really, really high kinetic energies, the mass becomes negligible. They kind of look like massless particles, almost. So the energy, total energy, the momentum, the kinetic energy, to 3 or 4 significant figures, they're just all the very same value. And so the momentum here would be the 1.30. Now what we could do is, just to see how fast they're going, to get a gamma factor, we can do 1 plus k over mc squared. And putting the numbers in, these have gamma factors of 2,545. Putting those into our formulas for velocity from special relativity, these electrons are going 0.999923 times the speed of light. So they're getting pretty close to the speed of light. Now in terms of their wavelength, putting that 1.3 GeV into 1,300 MeV, dividing through, it's coming in at about a femtometer. Now let's think back to the nuclear physics chapters that we just finished up. What's the size of a nucleus? Remember, the atoms are enormously large compared with the nucleus. Well, the nuclei that we looked at were typically several femtometers across. So we're getting down to the size. We treated the proton, an individual proton, as having a diameter of a couple of femtometers. And so these electrons are going to have wavelengths smaller than the size of a proton, and that means that they could be used to sample whatever the proton is made out of. They can react with the particles that make up the proton itself and identify the properties of those particles. So that's kind of the whole idea. Now, when I was at the Stanford Linear Accelerator in the 1980s, so you know, like 20 years after it was first built, by that time they had created a storage ring for electrons and anti-electrons. So our experiment actually had circulating beams of electrons and anti-electrons in a ring that was a couple miles in circumference. And the energies that we worked with were 14.5 GeV. So our energies were more than 10 times larger than what they're referring to here. And since we had electrons and anti-electrons both, the combined available energy, 14.5 plus 14.5, was 29 GeV. So significantly higher. And then after those times, eventually the Stanford Linear Accelerator went up to energies of 50, 60 GeV or higher. Okay, so that's kind of an idea of the experiments. This is just referring to the magnetic fields have to, the engineering that goes into these accelerators is extraordinary. You have to be able to control the magnetic fields so that the particles, as they go faster and faster, as they get higher and higher energy and higher momentum, that they continue to be guided along that path. And here's a picture showing how the particles can be accelerated. What you can do is you can set up different regions that are positive or negative, and then by synchronizing that, you could take an electron, for example. This is like the Stanford Linear Accelerator Center. You could take the electron and have it drawn towards the positive charge, but then once it comes through here, you could flip the signs, and then it's drawn towards the next segment. Okay, and then as they go faster and faster, you have to adjust for that. You either have to switch the charges on these regions faster, or you have to change the lengths of them to adjust for the electrons so that they continue to be to speed up. Now here's the largest accelerator on the planet. This is on the French-Swiss border outside of Geneva, Switzerland. Or maybe it's not. Let me see. They're referring to the Large Hadron Collider, I believe. Yeah, so I think this is what's called the Large Hadron Collider. It's the largest accelerator on the planet, and it reaches energies of 14 TeV, which is like TeVs are 1,000 times bigger than the GeVs. So these are where the highest energy fundamental particle reactions have been run. Okay, let's take a look at some protons at relativistic speed. So again, what we're doing here is looking at protons. So let's bring a proton up to speed. How much energy does it take to take a proton starting at rest and bring it up to 90% of the speed of light? And then part B says, okay, once you've reached 90% of the speed of light, how much additional energy is going to be required to bring it up to 99.9%? Now, which number do you think is going to be bigger? Let's take a look and see. And so let's just try these different speeds. So I'm going to say here are 3 different speeds. This is the speed at rest. This is 90% of the speed of light. This is 99.9% of the speed of light. And remember, from relativity, if we want to think in terms of how much energy do the particles require, we want to calculate gamma. So let's go ahead and here's our formula for gamma, if you remember, and here's how we're calculating kinetic energies. So these are the formulas we're going to make use of. Now, calculating the gamma, particle at rest has a gamma of just 1. How much does that gamma increase if we bring that particle to 90% of the speed of light? And bringing it to 90% of the speed of light raises the gamma factor. The gamma factor is now 2.29. So the overall energy has more than doubled. It's gone from 1 to 2. And now there's more kinetic energy than there is mass energy. Now, what's the gamma factor if we go to 0.999? Well, that's an even larger, by a significantly larger increase. So going from rest to 90% of the speed of light required the gamma factor to go up by 1.19, but going to 99.9 required an additional 20.1. Okay, and so how much kinetic energy? Using the formulas we have for the kinetic energies. So here is the mass energy of the proton. mc squared is 938.3. There's a kinetic energy here at rest. The kinetic energy would be 0. Once we get to here, this should be 2.29 minus 1 would be 1.19. And that 1.19 times the 938.3 gives us 1.12. And then we've done the same thing for the kinetic energy at 99.9. So you can see the kinetic energy needs to go up by, 1 GeV to get to 90% of the speed of light. But it's got to go up to 20 times as much, almost. So, bottom line, a proton traveling at 99.9% of the speed of light has 20 times the kinetic energy as one traveling at 90%. Okay, so as you go to higher energies, you can store more and more energy in these particles. Now, particle physics is kind of interesting. Particle physics is based not just on the particles that make up stuff around us, but it looks at particles that make up the forces in nature. What makes up an attractive force? What makes up a repulsive force? And the example they're using here are pillows, really? So it says it's a pretty crude analogy for how particles exchange energy. The idea here is force particles are able to push objects away each other because they transfer energy and momentum between the two objects. And so that's what these kids are doing here, right? They're transferring energy and momentum by throwing these pillows or whatever. In this case, they're using the pillows as a way to pull themselves together. So the force particles are things like photons. So photons actually make up the electric and the magnetic forces in nature. It seems funny to say that, but the electric and the magnetic forces are actually made out of particles. And so when something is, through electric or magnetic forces, when objects are either pushing away from each other or attracting each other, that's done by those particles kind of holding on to the photons and transferring energy back and forth through those particles. This is what it looks like in terms of a diagram. Now this is turned around a little funny. We're going to go ahead with the diagram the way they've drawn it. So it says this. It says if we have, here's an electron traveling along, and notice they're saying time is, on this diagram, time is in the upwards direction. So here are two electrons that come near each other, but then they push away because, hey, they're both negatively charged. What's going on at the fundamental particle level is that they are transferring energy and momentum through a photon. So there's actually a photon that connects those two electrons. And you might ask, well, can we see the photon? Can we see this photon that's transferring this energy and momentum? And particle physics says, no, you can't see it because it's not reacting with your eye. It's not reacting with a machine. It's exclusively reacting between the electrons. And these are referred to as virtual particles. So these virtual particles enable the transfer of energy and momentum between the other matter particles. So let's get into this, some real particle physics here. So let's get everything organized. So there are what we call matter particles, and there are what we call, these are just the matter particles. So we're going to do the forces on another sheet. Within the matter particles, there are what are called leptons, and there are what are called quarks. Now, initially, the leptons that were initially observed were, well, the electron. And then later on, the neutrinos. And then there's a heavier version of the electron. And there's an even heavier version of an electron. So what we refer to this as is, we refer to this as different generations of the leptons, and we're going to find out there are different generations of quarks. So these fundamental matter particles, the leptons and the quarks, they come in pairs. And so the electron is the charged version of the lepton, and the neutrino is its neutral partner. And then there's a heavier version of them, and that's the muon. And now this is also referred to as a neutrino. And so we start putting subscripts on the neutrino because experiments showed that the electron neutrino and the muon neutrino are not the same particle. They're both neutral, but they're not the same thing. And so we've identified independently, well, certainly the electron, and then the heavier version, the muon, and the even heavier version is called the tau. So those are the charged leptons, and then we have experiments that confirm the existence of 3 different, what we call flavors of neutrino. So there's 6 different flavors of lepton. 3 of those are charged, the electron, the muon, and the tau. 3 of those are neutral, and those are the 3 flavors of neutrinos. Now what we start to do is kind of organize these by properties. All of the leptons are spin-half particles. So, you know, this traces back to when we were looking at electrons in atoms, and we said they could be spin up or spin down, and the electrons carry that spin with them everywhere they go. Well, the neutrinos also are spin 1/2 particles. All of these leptons are spin 1/2. Now, when we were looking at nuclear decay, we saw that there were reactions where electrons could be turned into neutrinos, and I think we may have looked at some examples too, maybe we haven't yet, where neutrinos can be turned back into electrons. So these different flavors of leptons in reactions can actually change flavor. They can, we can take a neutrino and turn it into a charged lepton, or take a charged lepton and turn it into a neutrino. Now there's a second set of fundamental particles. In addition to the leptons, there are what we call quarks. So quarks were suggested in the 1960s, and experiments, kind of like what we showed with the Stanford Linear Accelerator, taking those high energy electrons and just running them into protons, were able to demonstrate within the proton, within the neutron, the existence of quarks. So protons are made out of 3 quarks. The quark flavors that we've listed here, we've listed them by letter, U and D and C and S and T and B. Well, they actually have names. The quark flavors are down and up in that first generation. And then there's a second generation of strange, that's the S, and charm. Now, the way this worked historically is that in the original quark model, quarks were introduced up and down to create the properties of the protons and neutrons. There were several different models that were suggested. The quark model had a lot of promising features to it, and the experiments eventually showed that the quark model had reliably described what is going on inside protons and neutrons. Now, if you look at the charges here, let's go back and do a quick comparison. The neutrinos were neutral, so they have no charge. The electrons, muons, and taus, they have a charge of -1 So that's familiar enough. One of the strange predictions, one of the unusual predictions of the quark model, was that it predicted that these quarks had fractional charges. And no one had ever observed a fractional charge on any particle. But the suggestion was that the ups would have a charge of +2/3, the downs would have a charge of -1/3. These are also spin-half particles. And so if I take 3 spin-half particles, how could they be combined? And it turns out that there are ways to vectorially combine the spins on the 3 quarks so that the proton overall would have a spin of 1/2. So we can take the 1/2 spin and the 1/2 spin, and we can cancel out one of the 1/2s, and we can show that we can get 3 quarks combined to give us spin 1/2 protons and spin 1/2 neutrons. And that's what we observe. And so the quark models correctly predicted how the spins would behave. What about these funny charges? Well, the idea is that a proton could be up, up, down, in terms of its flavors. A neutron would be up, down, down. Now, taking plus 2/3 plus 2/3 minus 1/3, that combination would give us an overall charge of +1, the charge of a proton. And for the neutron, by using flavors up, down, and down, that would be plus 2/3 minus 1/3 minus 1/3. That would give us 0. So the idea was the charges add up correctly, the spins add up correctly. Earlier in the course, we've mentioned that the magnetic fields of the proton and the neutron has magnetic fields. That was one of the indicators that something was going on inside neutrons. Neutrons were somehow made out of charged particles. So we are able to understand the anomalous magnetic fields of the protons and neutrons in terms of the individual magnetic fields of the quarks. So, the fundamental particle list, electrons are fundamental, neutrinos are fundamental, protons and neutrons are not. Protons and neutrons are made of quarks, and it's the quarks that are the fundamental particles. So, but as you noticed, we've gotten through most of physics without having to deal directly with quarks. And that's because of the strong force, the nuclear strong force. I guess we want to talk about this some too. The nuclear strong force is made out of particles that we call gluons. Yeah, that was named after glue. Remember, this was the 1960s. And so the gluons in here are represented by these kind of curly, springy particles. So the gluons are constantly being exchanged between the quarks within the protons and the neutrons. And the strong force is so strong that it's very, very, very difficult. Only under these really high energy experimental conditions do we actually observe the properties of the individual quarks. So we can get through almost everything that we've done in physics. We haven't talked about quarks at all. We've spoken many, many times in terms of protons and neutrons, and that's because these quarks are being held together so tightly that the protons and neutrons, for practical purposes, become fundamental particles. All right, quarks, in addition to their charges and their spins, they also have a property that we call color. Now, this property of color and the property of flavor, those are just kind of fun names that researchers back in the 60s and 70s came up with. And so what they're really referring to here is that quarks can consist of, there are these three possible quantum states that quarks can exist in. It's kind of like electric charge, I guess. Instead of having plus or minus charges, there are 3 different color charges that the quark can exist in. Now, just for fun, they were named red, green, and blue. So what we do is we say that why 3 quarks? Why is it that there are 3 quarks that make up protons and neutrons? Why don't we have 2 quarks or 4 quarks? Or why does it have to be 3? And the models that were developed, the mathematical models that were developed, explain this in terms of these 3 color states, that the force between the quarks is only attractive if we have 1 quark in each of the possible color states. So it would be equivalent to saying the force is only attractive if I have a positive and a negative charge. So for the strong force, the force is only attractive between the quarks if I have 1 quark in the red state, 1 quark in the green state, and 1 quark in the blue state. So that means that only certain combinations of quarks are attractive, and the states that, the patterns that are attractive are really, really held together firmly. So what we see are groups of 3 quarks together, and they're practically impossible to separate those out and look at the individual properties. Did we get to everything on this tape? This had a lot of stuff in it. So this is basically it. This is Well, it's not the whole story yet, but we've looked at all of the matter particles. So these matter particles are conserved. Now, when we say that they're conserved, we say that, you know, an electron could turn into a neutrino. The neutrino could turn back into the electron, but they can't just disappear. You can have a particle-antiparticle pair that come into existence, or you can have a particle-antiparticle pair that go out of existence. But you can't have an individual particle or an individual antiparticle just form out of nowhere, whereas we're going to find out with the force particles, those are created and those are annihilated. Okay, so getting back to the strong force. So let's take a closer look at this. The mathematics, the models that were developed in describing quarks, come up with two patterns of quarks that are stable, that are attractive. I don't want to use the word stable because we have to be careful about which of these particles are stable, which are not. There are patterns that we've looked at, that we talked about briefly, saying that there are these three color states, and when I put one quark in each of the color states, I get a very, very attractive force holding those three quarks together. Particles that are made up using these three quark pattern are referred to as baryons. Bary means heavy. And protons and neutrons are the most common examples. Now, of all the baryons, and researchers have discovered hundreds of these baryons. So these have been different combinations of these quarks have been observed for many, many years now, since the 1950s, really, I'm thinking. And the lowest mass versions of these are the proton and the neutron, and it's only the proton that's stable. The neutron actually decays into a proton, and that says that a down quark can turn into an up quark. And that would take a neutron and turn it into a proton. Let's see, the other broad category of quark-based particles are called mesons. So we've got a bunch of baryons that have been discovered. They all consist of quark, quark, quark. One in the red state, one in the green state, one in the blue state, but they have different flavors. So coming back to the chart here, that's what we need to include. So in addition to this first generation of ups and downs, which make up the protons and neutrons, there are second and third generations of quarks. The second generation consists of what we call a strange quark. Now, initially, when the quark model was first presented, it was based on up and down in terms of protons and neutrons and some other particles that had been observed. But it needed a third quark flavor in order to explain some of the other particles that had been discovered. Now, when researchers saw that third quark, they realized that to make the entire theory consistent, they needed a fourth quark. The quarks had to come in pairs. And so at that time, there were a couple of leptons known, a couple of generations of leptons known, and theorists suggested that the researchers start looking for this charm quark, and the charm quark was discovered. And so that's why it's called the charm quark. It's kind of like, hey, if this quark is out there, it's going to work like a charm. Everything is going to fit together perfectly in this model of leptons and quarks. But what you can see from the table here is, since that time, there has been a third generation of leptons that were discovered. The tau lepton was discovered, and pretty soon the B quark was discovered. And so the idea was there's got to be at least one more generation. Now, other experiments that have been done since that time suggest that there's a good chance that there are no more generations of quarks or leptons. We have gone to much, much higher energies. And if there was a fourth generation that existed, it's typically felt that we would have seen it by now. We would have been able to observe that. They have not been observed. So there's one possibility out there that we have identified all of the generations of leptons and quarks in nature. Now, a little, something about these names, up and down, you can kind of see how that was an easy, kind of fun set of names to use in describing the protons and neutron quarks. And then we went on to some more interesting names, strange and quark. And then when the third generation was first suggested, researchers named this beauty and truth. So the B quark is the beauty quark and the T quark is truth. But I think at some point people got a little embarrassed and they started calling them bottom and top. Anyway, sometimes you'll still hear this referred to as the beauty and truth quark, but more often I think now it's referred to as bottom and top. Okay. Now another one of the items that I guess we can talk about on here too is, let's see, electrons. Those were first discovered way back 1899, something like that. Neutrinos were predicted like the 1920s. They weren't directly observed for about 20 years. But you can see what's going on in particle physics is theorists have looked at the way the particle interactions behave and made suggestions as to what particles should exist. And then, experimentalists have gone in and set up experiments trying to see if those particles could be observed. And this is, has been a very successful endeavor. One by one, at the time the models were first put in place, there were really just a few of these particles. Since that time, the charm has been discovered, the bottom, the top, the tau, 3 generations of neutrons have been established. It's just been a remarkable success in terms of making predictions and then going in and finding out that those predictions really work. So these quark-antiquark combinations are called mesons. So the baryons, those are just quark, quark, quark. But it turns out that you can also, according to the theory of strong interactions, you can have an attractive force if you have a quark-antiquark where one of the quarks is in a particular color state and the other quark is in the anti-color state. So in addition to having blue, for example, there is what's defined as being in the anti-blue state. So antiquarks have anti-color. And so blue and anti-blue also become attractive. So red, green, the statement here is that the attractive forces occur for colorless combinations. So if you put one quark in the red state, one in the green, one in the blue, that becomes a colorless combination in the same way that if I had a positive charge and a negative charge, the combination would be neutral. Here, it's just the blue and the anti-blue that cancel out. Now, the simplest examples of mesons would be using the ups and the downs. So an up anti-up or a down anti-down is referred to as a neutral pion. And the mixture between up and anti-down and anti-up and down, those are referred to as the positive and negatively charged pion. And you can see their masses are similar in the same way that, say, protons and neutron masses are similar. Right? So in some sense, these are kind of made up of the lightest sets of quarks. Now what's interesting about this is that none of the mesons are stable. There are no stable mesons in nature because eventually the quark and the antiquark, they're going to react with each other. And so there are no stable mesons. There's only one stable baryon, and that's the proton. So of all these hundreds of quark combinations that have been observed by researchers, only the proton is stable. The neutron's pretty close. The neutron has a lifetime of like 15 minutes. So on the table here, what is it that's stable? Well, The quarks don't really exist independently. They exist as baryons or mesons. Only the proton is the only stable combination of quarks, and only the electron and the neutrinos are stable among the leptons. So there's really just a handful of stable particles. Okay, let's see how we're doing with time here. At some point we definitely want to take a break. Okay, so let's take a look at the forces in nature. So the forces in nature, as we were saying, are made out of particles. That's a really weird statement, but the electric and the magnetic forces are made out of photons. And this was really just understood due to the mathematics. Once researchers started looking at the way that energy and momentum was being exchanged in these particle reactions, they realized that it matched up with the way the electric and magnetic forces work. So eventually, there was developed what's called quantum electrodynamics, QED, and that's a description of how the electric and magnetic forces are made out of photons. Now, that was such a success that the other forces in nature, the weak force and the strong force, it was thought maybe we can come up with analogous mathematical descriptions of how these forces work. And this unification occurred back in the, and maybe not unification, but the completion of these mathematical descriptions occurred back in the 70s. So we now have what we think of as being a mathematically consistent description of the electric and magnetic forces, of the weak force, and of the strong force. Now the weak force, we've seen this when we looked at beta decays with in nuclear radioactivity. And so these forces are mediated by particles called the W plus, the W minus, and the neutral Z. And when you see the Z, you figure we're getting close to the end, right? So instead of a photon, which is massless, the weak particles are actually really high mass particles. W's and Z's have a mass that's like 100 times as much mass as a proton. So they're among some of the heavier particles in this standard model. The strong force, these gluons that are holding the quarks together, are expected to be massless. So the mathematical descriptions we have for those are that the gluons are massless, the photons are massless, and that there's not just one kind of gluon, there's actually these 8 related mathematical descriptions for the different gluons and the way that they carry color with them, the way that they mediate the color interaction, the color states of the quarks. Now, in addition to the electric and magnetic forces, the weak force and the strong force, at that point it was recognized that the standard model still was not mathematically consistent, not entirely. If you've taken calculus classes and if you remember doing series in calculus classes, you may remember that there are these mathematical series that either converge or they diverge. And what was happening in the standard model was, if you did calculations for some of these reactions, you couldn't get an answer. There was no way to get a meaningful, finite answer. And so some of the infinities, some of these diverging numbers needed to be, there needed to be something added in that would cancel out all of the diverging effects. And Peter Higgs, mathematician, physicist, back in the 60s, mid-60s, late 60s, came up with a mathematical description of just one additional particle that would eliminate all of the inconsistencies that had developed in the electric and the weak and the strong force models. So this one additional particle was able to eliminate all of the contradictions within the model, and it was referred to as the Higgs boson, and it was discovered. This has been now 15 years ago maybe. So this was kind of a last piece of the puzzle. All these other pieces were in place. There was something obviously missing that was connected to all the others, and this Higgs force, or this Higgs boson particle, turned out to be just exactly the right mathematical piece to make the theory complete. Now, a lot of times you'll hear that gravity, we don't have a quantum description of gravity. There's been a real effort underway for 40 or more years trying to come up with a model for gravitons, something that would describe gravitational interactions in terms of particles. We don't have that. So gravitational interactions are not part of the standard model. Let's go ahead, maybe let's take a break right there. I'm going to stop, and let's take a break for 10 minutes, and then we'll come back and finish up the rest of the chapter.